In this very important video, we're going to talk about several strategies for integration. Integration is, I should say, different from differentiation. So when you have a function, we can follow certain rules to find the derivative. But that doesn't work always for integration because there may be some nice functions, what we call elementary functions. But when you try to integrate, there you cannot find the answer using elementary functions. So that means the integration is kind of complicated. So the best way to do integration is, I should say, we need to identify certain patterns. So if you identify those patterns, then you can easily integrate. So we can start with this. So the first step is we identify certain patterns. So before we identify certain patterns, let's recall some of the things that we did earlier. So we're going to start with what we call common formula. So what are the common formulas that we have? So again, so we're gonna identify certain patterns. That's the first thing. And under that, we're gonna go with common formula. So we're gonna start with the four major formulas. So I'm gonna call this a power rule. So let's talk about the power formulas. Uh, so power formulas. Okay, powers. So what we have is the general power rule. So just the power rule. So xn. Um, dx. So when you want to integrate, you know that this is x n plus 1 divided by the same index n plus 1 plus c. This works when n not equal to -1. And then if n equal -1, we have this rule. So 1 over x dx, that doesn't follow the general pattern. So this is natural log x. Don't forget the absolute sign plus c. And then we have the exponential functions ex dx, which is equal to ex again, because we know that if you take the derivative, you get ex back. So now we go backward. And then what we have is some other base, like let's say you have another base b to the x dx. So the how we do this? So when b equal e, we have the result, but when you have just b, general b, then it is bx, like as in ex, but you have to divide by a natural log of b plus c, and make sure that b is not equal to 1, because b equal to 1 is going to create a problem here, because ln 1 is 0. Okay, these are what we normally call the power rule. 1 over x is also one of the power rule because x equal -1 case. Okay, now we're going to move on to trigonometric formulas. Let's discuss that now. So in trig formulas, we're going to start with sine cosine. So we have sine x dx, which is equal to negative cosine x. The reason is when you take the cosine derivative, you get negative sine plus c. And then we have the cosine x dx, which is simply sine x plus c. And then I'm going to include the hyperbolic functions here because they are because of similarity. So if we have a hyperbolic sine, so what we call shin x dx, which is simply cos um, x plus c. And similarly, when we have cos x dx, which is simply shin x. So you can see that there are no negative sign in those. That's the difference here. No negative signs. And then let's go to tan, cotangent, secant, cosecant. We have tan x dx, which is natural log secant x plus c. And then we have cotangent x, which is natural log sin x plus c. And remember, there are absolute sign in both. And next we have secant and cosecant. So secant x dx equal ln secant x plus tan x plus c. And then the cosecant x has two formulas. One is ln secant x minus cotan x plus c. Or you can put the negative sign outside. So minus ln cosecant x plus cotan x. So there are two formulas. One inside the negative sign, one outside the negative sign. Then we're going to go to the other formulas for secant and cosecant. So we have one from the derivative properties. We know that the secant, when you take the derivative of tan, the secant squared, so we can go backward. So secant squared x dx equal tan x plus c, and the cosecant squared x dx equal negative cotan x plus c. And we also have these two. We have secant x plus tan x dx, which is the derivative of secant x. So we have that, and also we have cosecant x plus times cotangent x, and what is this is the derivative of negative cosecant x plus c. Those are the common trigonometric identities. Okay, so there are um, I should say four different groups. So this is the first group, and the second group, and the third group, and the fourth group. Okay, now let's try to move on to the algebraic integrals. So we have these four algebraic integrals that are very important. So the first one is very important. It is dx divided by x squared plus a squared, which is 1 over a tan inverse x over a. And the other one is the dx divided by a squared minus x squared. Remember the order. It is a squared comes first, and there's a minus sign, and there's a square root, which is sine inverse x over a plus c. There's no 1 over a term there. And then we have dx over x squared minus a squared, so which is the negative sign. With the negative sign, so it is different from tan inverse. It is 1 over 2a natural log x minus a over x plus a plus c. You can prove this using partial fractions. So if you use partial fractions, you can prove this one. Okay, so partial fractions. And then we can also have another formula. It is dx divided by x squared plus or minus. So that means if you go with the plus sign, you have to use the plus sign on the other side. If you go with the minus sign, you have to use the minus sign on the other side. So which is natural log x plus x squared plus or minus a squared square root plus c. So those are like four common formulas that you can use in the future. Okay, now what we can do, we can discuss those different strategies one by one. Next, talk about those strategies one by one. First, we're going to start with identifying four formulas. So that's one of the trick that we use, what we call the four formula trick. So let's start with that. So the identifying with four formulas. Identifying with four formulas. So this gonna make most of the integrals like much easier. So we can identify it with four common formulas. So let's list them one by one. First one is the general power rule. So this works when we have function to some power and its derivative, and this works when n not equal to -1. The next, let's talk about what if n equal -1. For n equal -1, we have this result, which is f prime x over fx dx, which is equal to natural log the absolute value of fx plus c. Then we have the exponential function situation. So when you have an exponential function e to the fx f prime x dx, which is simply equals to e to the fx plus c. And then the last one, actually last one is one of the special case of a, but we can list this as a special situation because this is very useful when you try to do integration by parts. So let's write that. So this is ax plus b to the nth power dx. So what's going to happen, you can see this is just fx equal ax plus b. The derivative is simply a, so we can multiply and divide by a. So that means if you use a, part a, we can simply write this solution as the integral as ax plus b to the n plus 1 divided by that you multiply and divide, so that means that a is here times n plus 1 from the power rule plus c. So again, this doesn't work for n -1. Okay, so these are the four formulas that we're talking about, and if you remember, then you can solve many problems very easily. So let's do four examples, just to few examples, just to see how we can use them quickly. So let's talk about that. So as the first example, let's do this one. Um, so let's say we're going to integrate x minus 1 divided by 3x squared minus 6x plus 7 square root dx. So if you get a problem like that, what are you going to do? Are you going to identify the, actually you can simply do this problem using the use substitution method, but we can do this problem much quicker using the four formula trick. So if you look at the inside function, which is 3x squared minus 6x plus 7, the derivative is 6x minus 6. So you can see that only what you are missing is just the 6. So that means you can write this one as 1 over 6, and you can multiply inside by 6, so you can write it like that, and then we can bring this to the top. So this is 3x squared minus 6x plus 7 to the negative 1/2 because it's a square root dx. Now you can see this is just the four formula trick number 1. So you have function, that's a function, and you can see the derivative. There's a function, and this is simply the derivative of that function. So according to the four formula trick number 1, so I'm just going to say ff. You can see 1 over 6 still there, and here you can just consider the function, which is 3x squared minus 6x plus 7. So you add 1 and divide it by that, so that means 3x squared minus 6x plus 7, you add 1, that means you can 1/2 divided by that same power, so like that, plus c. So it's simply coming from the power rule, just the four formula trick. And if you can simplify this a little bit, you can see you get 1/3, so that means 1/3 it is 3x squared minus 6x plus 7 square root. That's much better if you write like that, plus c. So that's the answer, simply using the four formula trick. So you can see it's much quicker like that, but you can still do this problem using the substitution method. So let's do another problem of this type. How about this one? So let's say you have 0 pi over 2 sine theta divided by 1 plus cosine theta d theta. Now if you get a problem like that, you're going to look like it's a trial and error situation. So what are you going to do? You check the two functions, and we try to match with one of the formula, and you can see that the top is the derivative of the bottom function. So if you take this part as f, and you can see this is very close to the derivatives, this is just the negative derivative. So negative is just a sign. You can multiply and divide by the, like, you can multiply inside outside by negative sign to handle that, and then you can simply see the derivative there. So that means we can do it like this using the four formula trick again. So I'm going to put a minus sign inside and outside, so like that. So that's the preparation that we do for this problem, and then 0 pi over 2, and then you can see that now directly the top is the derivative of the bottom function. So according to the formula number 2, for formula number 2, so I'm going to say for formula is a minus, that's already there. So this is simply natural log the bottom function. Okay, so you can write it like that if you identify that, and then you just need to evaluate because it's a definite integral, you don't add the c here, evaluate at pi over 2 and 0. So negative, so let's evaluate. So if you put pi over 2, so ln 1 plus cosine pi over 2, which is 0, minus ln 1 plus cosine 0, which is 1. So you can see this is equals to 1, this is equal to 0, and then we know that ln 1 is 0, so that means this term is 0, so this is gone. So you only get ln 2 with the negative sign. This simply becomes ln 2. We don't need the absolute sign because it's 2 is positive. So that's how we do it quickly using the four formula trick, and you can see that it's much faster if you remember the four formula trick. Again, you can still do this problem using the substitution method. For this one, you can substitute u equal 1 plus cosine theta. For the top one, you can see you can substitute u equal the inside function 3x squared minus 6x plus 7. You can still do it, but we have a shortcut right now. Okay, And then you can try this problem as a practice problem. Uh, so yeah, try this. So we have x squared minus 6, x squared minus 2x plus 2 divided by x3 minus 3x squared plus 6x plus 1. So what you want to do is you can match this with one of the formulas. Okay. So this is something you can do. And as the next example, you can try this. So as a second example, you can try e to the tan inverse x divided by 1 plus x squared dx, and you can see this very well match with one of the formulas there. Okay, and then you can try these two also. So we have square root 4x plus 3 integral, and then also we can have let's say 1 over 2x minus 3 dx. Okay, so you can try these four as practice problems. As the second method, we can talk about simplifying techniques. So let's do the second one. What we do here is simplify. So simplify. So simplify is like a kind of major method. Under simplify, we can talk about four techniques. So the first one is I'm going to call this split. So there are some problems once you split, you can do it. So this is split. And the second technique is multiply or divide. Multiply or divide depending on the problem. And then as the last one, multiply by conjugate. That's also a good technique. Um, so multiply by conjugate. Okay, let's try to do some problem using these three techniques next. So as the first example, let's do this one. So let's say we have x plus 3 divided by x squared plus 4 dx. Something like that. So you can see that top is not the derivative of the bottom function, so you cannot directly use the technique that we were doing. But what you can do is, as the first step, we can split this into two integrals. So that's the first step. So we can split this. So we can write this one as x over x squared plus 4 dx. That's the first one. Plus the other one is 3 over x squared plus 4d. That's the first step. So what we did, we split them. Okay? So we split, and then after that, now we can do it, because you can see the first one is simply the one of the four formula trick or the substitution method or use up. Second one is one of the formulas, the algebraic formula from tan inverse. So we can do the manipulation here. So we can see the 2 is missing. So we can do 1/2 2x x squared plus 4 dx, and here what we can do, we can simply pull 3 out. So once you do that, now we can see this gonna match with the formulas. So the first one is simply from the four formula trick. The top is the derivative of the bottom function. So this is the f function, this is f prime. So that means we can write the formula. So this is simply going to be 1/2 natural log, you can see x squared plus 4. We don't need the absolute sign here because this is positive. And here what's going to happen is, this is just the tan inverse formula. Here a equal to, so that means 3 over 2 tan inverse x over 2, that's a, plus c. So that's the formula. Very quickly, so what we use is we use the four formula trick for this problem, and the major technique was split. Okay, so let's do another one. So how about this problem? So we have let's say we're gonna do square root x and then 3 plus square root x, something like that. And when you see this problem, you can see this is a product. Unfortunately, there are no product rule in integral calculus. So what you're going to do is we can distribute. So you're going to multiply through. So let's distribute. So you can multiply inside by this one. Okay, so you can multiply this term and that term both. So let's do that. Once you do it, you're going to get 3 square root x, and then plus when you multiply square root, you get x. So that's what you get. Now this is just one term. So you can integrate term by term. So if you do that, so this is 3. Uh, so this is 1/2 power. So that means x to the 3 halves over 3 halves. And then plus this is x squared over 2. We can simplify this a little bit to make it better. So we get 2. And you can write this one as x cube square root uh, plus 1/2 x squared plus c. Okay, so that's how we do it. Let's do another one with derivative, division. So how about this problem? So let's say we have x plus 1 divided by square root x dx. Again, there are no quotient rules in integral calculus. What we can do, we're going to divide. So you're going to go term by term. So this x over square root x. This step is unnecessary. You can just do the mental calculation here. We need a bracket there or parenthesis. Now we can simplify this. So this is going to be x to the 1/2, and this is going to be x to the negative 1/2. Now we can do term by term integration. So that means the first one going to be 2/3 x to the 3 halves. It's okay, you can leave like that. And this is x to the 1/2 divided by 1/2. That means multiply by 2. So you can get that plus c. So that's what you get for that one. But what we did was we divide. Okay, so the major step was we divide term by term division. Good. And then we can do this one. This may be a little complicated, but not that bad. So let's say integral of 1 minus x over 1 plus x square root dx. So you can see it looks little complicated. So there's expression with radicals 1 minus x, 1 plus x. What we can do, we can use the multiply by conjugate techniques for this one. So once you multiply by conjugate, you can make it something manageable, because here there are no formula. You can integrate term by term. It is inside another function. So the best thing would be multiply by the conjugate at the bottom. Okay, so we're gonna do that. So it is, so we have 1 minus x square root. We can split this first like that, and then I'm going to multiply by the conjugate of the bottom function. Okay, 1 minus x square root 1 minus x square root. Okay, it's a conjugate of the bottom function. Okay, it's very important. If you do top, you can simplify this that much. You can do something, but you're gonna get stuck again. Okay, now let's combine. So you can see there are some simplification going on. The top become the square root times square root, means it just become 1 minus x. And in the bottom, I'm gonna write this extra step here. 1 minus x square root, 1 plus x square root, 1 minus x square root. What you can do, actually, you can bring them inside. So you can combine them. If you combine them, you're gonna get 1 minus x. Inside, you're going to get 1 plus x times 1 minus x whole thing square root. So you can do that. You can bring inside the product. And then, now what we can do, you can see the bottom simply become 1. You can use the difference of squares formula. So once you use difference of squares formula, this is going to be 1 minus x. Inside going to be 1 minus x squared square root dx. Now what we can do is you can split them into two integrals. After we get to this level, you're going to split. So once you split into two integrals, you're going to be 1 over 1 minus x squared square root dx, and then minus the other one going to be x over 1 minus x squared square root. And you can see the first one we already know. The second one, what we can do is think of the derivative of the bottom function, which is once you take the derivative you get negative 2x. X is there, negative 2 you can multiply and divide. So that means we can write this one as, just going to repeat here, or you can just do the manipulation there. So what you can do is, so I'm going to do those changes here. So what we can do is we can bring the negative sign inside and multiply by 2 and divide by 2. I'm going to say 1/2 and pull the negative sign inside. Once you put the negative sign inside, then match with the derivative. So you can see it's the same thing, but just a simple manipulation. And you can see now it's going to work very well. The first one is simply sine inverse x plus the other one is just the general power rule. So you're going to get 1/2 already there. You can see this is 1 minus to the negative 1/2, so you're going to add 1. So the 1 minus x squared to the positive 1/2 divided by positive 1/2 plus c, and you can see 1/2 1/2 get cancelled, so you get sine inverse x plus 1 minus x squared square root plus c. Okay, so that's how with all these steps. So I didn't ignore any steps here. So now you can see how it works. It's not that difficult. So the major step was multiplying by the conjugate. Okay. So for this problem you can also try, so I'm going to write it there. So try the substitution. You equal the whole function 1 minus x 1 plus x square root. You can also try this one and you can see it's gonna work just as a u sub problem, but it's long. But here it's like much simple. It's not that bad. The math is not that bad. Okay, now we're gonna move on to the next technique, the trigonometric simplification. Let's talk about those trigonometric simplification techniques. So there's a separate video created for trigonometric uh, integrals, because those trigonometricals works in a different way. There's a one video actually called just for trigonometric integrals, but also there's another video just discuss with different type of techniques. So you can find a link in the description if that you can see. This for a special method for trigonometric integrals. Okay, so let's talk about those common techniques. So we can start with as the first major method would be the split. So we still use that. So that's the you can split the integral into several. So that's one technique. And then the second technique is rewrite as a common formula, because we know the common formula list. So what we can do is we're gonna see whether you can rewrite the integral as one of those common formulas. Then we can directly use them. So rewrite as a common formula. So that's a major technique, common formula. Okay, this is one of the major techniques. And then the next one would be we can rewrite using sine cosine. So that's another one. So we can say rewrite using sine and cosine. So because once you rewrite using sine cosine, you can simplify a little bit further. So that's another technique. And then also what we can do is we can multiply by conjugate. So multiply by conjugates. So that's another technique, especially when you see 1 plus sine x, 1 minus cosine x, things like that. So you're going to multiply by conjugates. So, that's a major technique for trigonometric integrals. And we can also do so we're going to simplify using trigonometric identities. So use trigonometric identities. Trigonometric identities. So those are the kind of common techniques that we're gonna use, and so let's see how we can apply them in certain problems. So let's start the first example. Let's also recall these three formula. This can be useful at times. So the first one is we're gonna see sine k is a constant, so kx dx, so which is simply negative 1 over k cosine kx plus c, and then when you have the integral of cosine kx dx, so which is the 1 over k sine kx plus c, and also we have one from the exponential function. We have e, a constant x dx. So what you're going to do is simply divide by the constant e to the kx plus c. So this can be very useful at times, and you can save a lot of time. So let's highlight them. So these three formulas are very common, so you can use them directly, and you can see you can prove them simply using the u sub method. Just take u equal kx and you can prove them. Okay, this is one of the so three of the three formula that are very useful. This only works when k is a constant, so the k which is a constant other than 0. So as the first example of this type, so let's do this one. Let's say we have the integral of sine x divided by cosine squared x dx. So you can see that the top is the derivative of the inside function. Here the inside function is cosine x. So if you pick u equal cosine x, you can simply use the substitution method here, because the top is simply the derivative of this function. But we're going to use a different technique here for this special problem. So what we can do is I'm going to see whether you can rewrite this as one of the common formulas. So let's pull one of the cosine and write with sine, and I'm going to leave the other cosine here. So these are special trigonometric tricks, and then you can see now the first one is the tan x, second one is the secant x. Now this is actually one of the common formulas, because this is simply the derivative of the secant function. So that means the answer is secant x plus c. So so that's what happened. Okay, so you can do this kind of tricks. So let's do another one that works similarly. So how about this problem? So let's say we have, so the next example. So let's say we have sine x plus cosine x square dx. So if you have something like that, what what is the obvious thing we can do? We can distribute. That's exactly what we can do. We can distribute. So once you distribute, so you're gonna get the square of the first term, so sine squared x, twice the product, and then we have cosine squared x, like that. Um, Now what we can do is you can combine these two. Once you combine these two, this is equal to 1. This is simply 1. So we have 1 plus. Now what is 2 sine x cosine x? 2 sine x cosine x is simply, this is one of the trigonometric identity. We know that this simply equals to sine 2x. So we can use that. So that means this is simply sine 2x. Now this is very easy to integrate. So if you integrate this one, you're going to get 1 means x plus, this is again one of the common formula. This is sine 2x. So that means we're going to divide by that. So what you're going to get is a sine, so that's a negative. So you're going to get negative 1/2 cosine 2x plus c. So that's what you get just using those common formulas. How about we have this one. Let's say we have tan theta divided by sine theta. So you can see that top is not the derivative of the bottom function. So maybe if you rewrite using sine cosine, it's gonna help. So that's what we can do. We can write tan as sine cosine. So we have sine theta over cosine theta. That's the tangent theta. And the sine in the bottom, so you can write it like that. And you can see that there's a simplification. You can see the sine get cancelled. So you're gonna get 1 over cosine theta, but 1 over cosine theta means secant theta. So we have secant theta d theta. The secant means, according to one of the formulas, this is simply a natural log secant theta plus tangent theta plus c, because this is one of the formulas that we can use. So this is how you do this problem. So what we did, we rewrite using sine cosine, and then there's a nice simplification going on. Okay, so let's do a little long problem now as the next one. So let's do this problem, and you can see this problem can be done in 3 different ways. Um, so we're gonna do tan theta divided by secant squared theta d theta. So again, as we did before, we can write this one using sine cosine first. So this is simply a sine theta divided by cosine theta. That's a tangent. And the secant means 1 over cosine. So that means you can write this one as cosine squared theta. That's a secant d theta. Now you can see one of the cosine get cancelled. So you end up getting sine theta cosine theta d theta. Now, after you get to that integral, you can do this integral in 3 different ways. So let's talk about those 3 techniques separately. So the first one is, so I'm going to write this one sine theta cosine theta d theta. The first technique is, you can see this as, you can see cosine as the derivative of the sine function. So you can say this is the function, that's the derivative. So that means we can just use a general power rule. So if you use a general power rule like that, so I'm going to write the first answer like this. So if you use general power rule like that, so the function is sine, then cosine is the derivative. So that means it's simply going to be 1/2 sine squared theta plus c. So that's happened uh, if you use f and f prime. So next one is what we can do, we can switch the order. So we can say this is the function and that is the derivative. You can see only the negative sign is missing, so you can say negative derivative. So if you do that, then you can also do it like that. So that means that's the second technique I'm going to say. So we have, so if you use the second technique is the negative. So what happened is you can see the derivative is the sine function. So that means you can write this one as negative 1/2 cosine squared theta plus c. So that's happened if you switch the order. So you can write cosine as a function, the other one is a negative. Um, so then simply use the power rule. So under the power rule, this is what's going to happen. So for the third technique, what we can do is I'm going to write here. For the third technique, what you can do is you can write this one as the using the double angle formula. So you can see if you look at sine 2 theta, it is 2 sine theta cosine theta. So the 2 is missing. So we can do is you can say 1/2. Then you can say 2 sine theta cosine theta d theta. Now what you can do is this is simply 1/2 sine 2 theta d theta. Now just use the sine formula. So this is a sine. So that means this is simply you can say sine means cosine. If you take the derivative is a negative cosine, so that means the answer going to be so we already have 1/2 here, and then you're going to get the negative cosine 2 theta divided by 2. Okay, so that means if you combine them, so what's going to happen? Negative 1/4 cosine 2 theta plus c. So that's the third answer. There are 3 different answers like that. and using three different techniques. Okay. uh, yeah, so that's the technique for so that problem. So yeah. So again, so what we did was first, for the first technique, I used the sine theta as the function, and the other one is the derivative. For the second one, I used the cosine as a function, the other one is a negative derivative. For the third method, we use the double angle formula, and then we can use the formula. So I'm going to recall those three formulas here that we use. So these formulas sometimes very helpful. So the one of the formula is when you have sine kx dx, k is a constant. So what's going to happen is this is negative 1 over k cosine kx plus c, and then we have cosine kx dx. Here k is so it's 1 over k sine kx plus c, and then also we have one for the exponential function e to the kx dx. So this is 1 over k e to the kx plus c. So those are the three formulas. So these are very common, and we use one of them here. Okay, so let's do a few more trigonometric integrals next. So let's do this one as the next example. How about we have cosine theta divided by tan theta. So if you get a problem like that, you first check whether the top is the derivative of the bottom function or the inside function. But it's not the case, so what we're gonna do is we're gonna rewrite this using sine cosine. Um, so this is, you can see this is cosine theta, and the bottom is sine theta over cosine theta d theta. Now what we can do is we can multiply the um, top and bottom by cosine theta. Um, so you can rewrite this one like this. So we can say so we have cosine theta, and then so we can write this one as, because it's a division, so you can write this one as cosine theta over sine theta, because the division is the multiplication of the reciprocal. So that's what we did. So we invert this, we just take the reciprocal here, so that's why it's upside down here. Now what we can do is, so you can see this is simply cosine square theta over sine theta d theta. We still don't see any special technique that we can try here. So what we can do is we can write the top using the Pythagorean identity. So we can write this one as 1 minus sine square theta over sine theta d theta. So we use the identity. We know that 1 minus sine square theta equal cosine square theta. So we use that here. Now what we can do, we can split the two. So if you divide by the bottom function, so 1 over sine theta, which is cosecant theta d theta, minus, you can divide, so that you can get sine theta d theta. So you can see, you can integrate them separately. First one is a formula, so we're going to say ln cosecant theta minus cotangent theta, minus, this is the sine means negative cosine, that means it's going to be plus cosine theta. So that's how you did the problem, and you can see we go through several steps. We use rewrite using sine cosine, and then we can use one of the trigonometric identity here to bring it to one type. Okay, so that's the step here. We rewrite this one using only sine, then we split. We're gonna divide, it's a 1 over sine, which is cosecant theta, and then we divide by sine the other term, you get sine theta, and then there are formulas and we get that. Now let's see how to do that. So there are some problems once you convert, you're gonna get to one of those formulas again, and then you can use this formula, this answer. Okay, so let's look at this problem now. So we have, so let's say we can do mm, sine theta plus cosine theta divided by tan theta. So again, so you can see this is a sine cosine problem. So actually, this problem is slightly different because you see a sum there. So the best thing would be to split this, unless you see a like kind of special simplification here. So let's split this. So once you split, you can see that this is gonna be sine theta divided by tan theta d theta, and then plus this is gonna be cosine theta divided by tan theta d theta. Now you can write as before, you can write this one using sine cosine. So this is sine theta. Tan means sine theta over cosine theta d theta. The other one is cosine theta divided by again sine theta over cosine theta d theta. Uh, and you can see the second term is the one we did before. So that means we know how to do that. Uh, so here what's going to happen is you can see the sine get cancelled, the cosine goes to the top. So that means, so this is simply going to be cosine theta d theta plus, so this problem as we did before, um, so you can see that, so I'm going to skip some step. Remember we get this one to 1 minus sine square theta sine theta in the previous problem. So I just repeat the same steps here. Now we know what to do. I'm going to copy the answer from the previous problem. So that means this you can write as the first one is the cosine. That means this is simply sine theta, and the plus this one we did before. So that means according to that problem, this is simply sine cosecant theta minus cotangent theta, and then plus you get cosine theta plus c. So yeah, so that's how you do it. So the major step was you split. Okay, so that's the major step we did. We're gonna split here. Okay, so split and then do two problems separately. So what you can do is you can try this problem as a practice problem. So so let's do this one. So I'm going to say exercise. So you can see tan theta plus cotangent theta over sine 2 theta d theta, and see whether you can simplify this and get this answer. You should get 1/2 tan theta minus 1/2 cotangent theta. Okay, so you may have to use the double angle formula for this problem. So what's the double angle formula? We know that sine 2 theta equal to sine theta cosecant theta. Okay, so let's just do trigonometric integrals are kind of complicated. So I'm gonna because of that I'm gonna do maybe two more problems before we move on to the next technique. So let's do this problem next. So let's look at one of the trigonometric integral that we discussed in the previous section. So you can look at more about this, and you can study more integrals in that special section. So you can see a link in the description. So let's try to do this problem just to recall what we did. So this is a tan cube x divided by cosine cube x dx. So this is clearly a trigonometric integral. So we can you can solve this problem in many different ways. So I'm going to discuss one special technique here. So what we can do first is just to show you one technique, we can write this as tan cube x, and then the cosine means it is cosecant x dx. Now you can see that the tan has an even power. Um, so we can do this problem using one of the common trick, that is u equal secant x. So that you can try. That's one technique. But we're gonna do in a different way. Um, when you see like a problem like that, what you can do is we can write tan using sine cosine. So if you do that, you can write this one as sine x over cosine x to the cube, and then so this is 1 over cosine cube x dx. Now you can write this one only using sine cosine. So you can see that this is sine cube x over cosine 6x dx. Now what we can do is, um, because you can see sine has a odd power, so what we can do, we can pull one of the sine out, and then you can use the u equal cosine substitution for this problem, because that's a kind of common trick for most of the problems like that. So that's why I'm going to use this technique rather than doing in the standard way. So let's do that. So what we can do, we can pull one sine squared term here, and then we have cosine 6x. So I'm going to write one sine term there just for the derivative. So the goal is to use u equal cosine x. Okay, using the sine has odd power, so we use the other type. That's what we normally call it. So now you can see, you can rewrite what we're trying to do. We can write the integral using cosine. That's the trick. So what we do is a negative. We can write this one as sine square. We can write 1 minus cosine squared x, and the bottom we have cosine 6x. And then we know that when you take the derivative of the cosine, which is negative sine, we know that the derivative of u is negative sine x. So so in the negative sign, that's the negative sign we put outside, so here we say negative sine x. So that the negative sign cancel out, and then you can see this is simply the derivative du, so we don't touch that part. And for the other part, we can substitute u. So if you substitute u, this is simply 1, the negative, this is 1 minus u squared over u to the 6 du. So it's very clear, you substitute for u. Now you can divide by u, u6. So if you do that, you're going to get negative the integral u to the negative 6, and then minus u to the negative 4. Now you can see, and du, this is very easy to integrate. So if you integrate, you get negative u negative 5 over negative 5, and the plus, because the negative negative become plus, u to the negative 3 over negative 3 plus c. And then if you substitute for u equal cosine, and you can see this is negative power, you can bring it up again. So that means you're going to be 1/5 secant 5 x minus 1/3 secant 3x plus c. So that's the answer using this technique, but you can also use the other technique. So I just wanted to show you what other techniques out there. Especially when you learn something, we are not just going to stick with one. So we can do one last problem before we move on to the other type. So let's do one last problem from trigonometric integrals. So how about this one? This is also another trick. So as the last problem of trigonometric integrals, let's do this one. So this is dx over 1 minus cosine x. So you can see that when you see this problem, the top is not the derivative of the bottom function. That means we can use any of those formulas before, and it's not clear. So what we do, we can use the common trick. When you see like 1 minus 1 plus sine cosine terms, what we normally do is we can multiply by the conjugate. So we can use that technique here. So so I'm going to isolate the term 1 minus cosine x. So what we can do, we can multiply the conjugate of that, so which is 1 plus cosine x, the top and bottom. So we're going to multiply by that and the dx. Now you can see this simplifies well. So what happened is we're going to get 1 plus cosine x, and in the bottom is simply going to be 1 minus cosine squared x dx. And then you can use the trigonometric identity here. So you can write this one as 1 plus cosine x. You can see 1 minus cosine and squared x means sine squared x dx. Now what we can do, we can divide the both terms in the top by sine squared x. So if you do that, if you divide by 1 over sine squared means cosecant squared x dx. And the other one I'm going to rewrite. So other one is cosine x over sine squared x. What we can do, we can rewrite this so that it's matched with one of the formulas in the table. So the first one we can actually already integrate, because this is the cosecant squared. That means the integral is negative cotangent x. So that part is done. Other one we're going to rewrite. So we can write this one as cosine x over sine x, and then 1 over sine x. And you can see now this simplifies, you're gonna get two formulas. So it's a negative cotangent x, and you can see this is simply cotangent x cosecant x dx, and this is one of the formulas in the table. So that means you're gonna get negative cotangent x. This is negative the derivative of cosecant x plus c. So this is how you can do this problem, matching with one of the formulas in the table. So we match with this formula, and we also match with that formula. So you simply match with one of the formulas in the table, and also we use the special technique, we multiply by conjugate. So we multiply by conjugate, and that's gonna solve the problem. So you can use same trick to several other problems. So why don't you try these problems as exercise? One is 1 over secant x plus tan x dx, and also see whether you can do this problem. This is not exactly this, but you can still try some manipulation. So sin x plus cosine x dx. Okay, so try to see whether you can try do these two problems. The first one is easy. It's a conjugate problem, but the second one you need to think about how to do that. Okay, so this is the end of trigonometric integrals. Now what we're gonna do, we're gonna move on to the substitution method. So as the next major technique, we can talk about the substitution method. So substitution method. So when you do substitution method, what we normally do is we're gonna identify. So identify u equal gx, and then the du function, du equal which is g prime x dx. So each substitution problem boils down to these two things. So we're gonna find the u function, and also we're gonna identify the derivative of that. So so let's do a couple of examples. Let's start with this one. So so let's say integrate 3 tan inverse x square root divided by 1 plus x squared. A problem like that. So you kind of need to train your eye for these problems. So see whether you can identify the inside function and its derivative. And you can see it's very clear here that u is simply the tan inverse x. And you can see once you take the derivative of this, it is simply 1 over 1 plus x squared and then dx. You can see everything is here. So now what we can do, we can use the new variable to write the problem, rewrite the problem. So we're going to take 3 out. So tan inverse x is u, so that means it's going to be u square root. And then you can see that 1 over x dx. dx over 1 plus x squared, which is exactly equal to du. So you can say it's du. So that's it. So that means so this is if you want to rewrite it, this is 3 u 1 half du, and then you can simply take the integral now. So this is u, so 3 halves divided by 3 halves plus c, and you can see 3 get cancelled. So divide by 2 means multiply by 2, so it's 2, and then u equal that, so we're going to put that back in. So you can see tan inverse x 3 halves plus c. Okay, so it's very simple. So what we did was we identify the function. So let's do another problem of this type. So how about this one? So this is sin x. Um, we did a similar problem using in Trig also, but this is very common, so I'm gonna repeat a problem like that. So so if you get a problem like that, so you can see this is a trig integral. Again, we can identify the inside function. In this case, u equal, you can see cosine x. Why we do that? Because if you take the derivative, it is negative sine x dx, and you can see sine x dx is there. It has to be in the numerator, so that's very important. This has to be the numerator. So what's gonna happen here is you can see you need negative sign, so we're gonna put the negative sign back in, and then write 5x dx. Now we're gonna substitute. So you can see negative sine x dx is into du, and then cosine is u, so that means u to the 5th power. So you can write this one as negative u to the negative 5 du. Then you can just use the power rule. So it's a negative, and the you add 1, negative 4 divided by negative 4 plus c. So negative get cancelled. So 1/4 u equal cosine. So that means cosine 4x plus c. So you can write it like that, or you can write the same answer using secant, because one of course I mean secant, so secant 4x plus c. So any of them are valid. Okay, because that's another trigonometric function. So you can see how you can use the substitution method to do certain problems that looks different, but you can bring it to the substitution method. So let's try to do a couple of more examples, because this is one of the interesting technique. So how about this one? So you can start, we're going to do this one. So it is dx over x ln x square root x. And again, you can see inside function is very clear now. So it is u equal ln x. And then du equal 1 over x dx. So you check whether you can find a function its derivative. So now after we do that, the solution is very clear. So you can see so ln x is u, so it is 1 over u square root, and dx over x is simply du. So you can rewrite this one as u to the negative 1 half du. So this is very easy to integrate. So it is u 1 half over 1 half plus c. That means 2 square root u. Square root u means ln x plus c. So very simple. So let's try to do a problem that doesn't look like that. So how about this problem? See this one. So let's say example, the integral 1 over x plus square root x dx. So maybe the substitution may not be clear very well, but so if you get a problem like that, what we normally do is we're gonna go to the smallest function, smallest power actually here. So you can see, so I'm gonna pick this one. So that's, you go for the smallest power. So I'm going to pick that one. So the u equal square root x. That's what we do. Um, so, and this also says that u squared equal x. And also if you take the derivative, so du, if you take the derivative, it's going to be 1/2 x to the negative 1/2 dx. In other words, you can write this one as 2 square root x dx. Okay, so we have everything we need. Now what you want to do is you want to pull out 1 over square root x term for the derivative part. So that we can do. Uh, so um, let's try to do some algebra here. So this we have this kind of special steps for these problems. So what is dx? So dx is, you can see 2 square root x du. But what is square root x? Square root x means u. So that means this can be 2u du. So we have the special simplification here. So that happens sometimes. Special simplification techniques. Now with this, now what we can do is we can substitute. So let's substitute. So if you substitute, what's going to happen now? It's 1 over x means u squared. Square root x means u, and then dx is 2u du. And you can see that one of the u you can cancel. So once you cancel that, if you cancel one of them, one of the u's, cancel one, and then one of them. So what you're gonna get is 2 over, you get 1 plus 1 du. You get only one of them, so u plus 1. So that's what you get. Now you can see this is simply the natural log. You can integrate that. So this you're going to take 2 out. So this is u plus 1 du, which is simply the natural log. So ln u plus 1 plus c. But we know that what is u equals square root x. So you can say it is square root x plus 1 plus c. So that's how you do that problem, and you can see there are special simplifications going on here. So you pick the u, and after that what happened was you kind of transform this problem to something that is easy to integrate. So that's where you end up getting. Okay, let's do another interesting problem like that. So how about this one? Let's say we have sine square root x dx. Again, the substitution is very clear, so we're gonna pick this one as u. Because once you do that, that part's gonna be like simple looking. So let's do that. So we're gonna see u equals square root x, and then again du. So du equal as before. This is gonna be 2 square root x dx. And then we try to find dx. So you can see that the dx is, we multiply the other side, 2 square root x du. If you plug in, it's a 2 u du. That's what you get. Now if you plug in that back to the problem, you can see this is sine square root x means u, dx is 2 u du. So if you rewrite this problem, you can write this one as, you can pull 2 out. You can see this is u sine u du. So if you get a problem like that, what we normally do is integration by parts. So you can use integration by parts to do the problem now. So you transform that problem into a integration by parts problem. Now we're going to use the integration by parts. So we can use a shortcut method now. D and I. So we're going to pick d as u and I as sine u. Take the derivative 1, take the integral, this is sine, so negative cosine. Take the derivative, take the integral, so this negative cosine means sine. Now we can multiply with First one is a plus sign, and then the rest is with a minus sign. So plus minus, and this is 0, so we don't get anything. So that means you can write the answer now. So it is 2 times, you're going to multiply the first 2, which is negative u cosine u, and then negative positive sine u plus c. And if you plug that back in, so it is 2 times sine u means square root x minus 2 square root x cosine square root x plus c. So that's the answer. So you can see you first transform the problem to a integration by parts problem, and then use the integration by parts to solve the problem. So here we use 2 techniques. Use the u sub and also use the integration by parts. See the special simplification here. So we transform the dx into this special type. Okay, so that's a special kind of technique. Okay, so what we did, we solve for u and solve for dx as well. We haven't done problems like that before, so this is something we need to remember. So let's do the next problem. So as the final problem of this type, let's do this one. This is ln x over x 1 plus ln x squared square root dx. And you can see in this problem also the u function is clear, u equal ln x, and then take the derivative, so it is 1 over x dx. So that means we can rewrite this problem as using the new variable. This is going to be u over 1 plus u squared square root, and then dx of x is du. So now under this problem is simple. So because you can write this one as u 1 plus u squared negative 1/2 du. You can see the inside function. So I'm going to use the 4 formula trick now. So you can also use another substitution if you want, but we can just get the answer easily now, because inside function is 1 plus u squared, derivative is 2u, so only 2 is missing, so we can say 1/2 2u 1 plus u squared negative 1/2 du. So according to the 4 formula, so you can see this is simply 1/2 1 plus u squared. You can add 1 and divide it by that. So this is the 4 formula trick here. It's much faster. Plus c, and then 1/2 get cancelled. So that means the answer is 1 plus u equal ln x squared. So we have square root plus c. So you can see you can get the answer very quickly, and if you identify the right substitution. Okay. So now let's move on to the other technique, what we call the special types. So there are special types that we want to go through. So let's talk about that now. So under special types, we're going to talk about first the trigonometric integrals. So we have trigonometric integrals. So we studied this earlier, so this is like a recall, and then under trigonometric integrals we studied sine some power x cosine nx dx as the first one, and then we went to tan nx secant mx dx, and then we talk about, and also similarly we can do cotangent nx cosecant nx dx, mx dx, and also finally we talk about products. So sine mx cosine nx dx. So those are the types we studied, and you can see a link in the description if you want to recall what we did in that section. So well, let's do only one example from this type, just to recall what we did. So so we can do this problem. So we have, let's say, tan 3x secant 7x dx. So according to theories we discuss, we know that when you get a problem like that, so you see that the tan has odd power. So if tan has odd power, we're going to try the substitution u equals secant x. So what we try to do, we try to rewrite the problem using this new substitution. So we first pull out a term for the derivative, because we know that once you take the derivative, you're going to get the secant x tan x. So that means we can isolate that term. So let's start doing that. So I'm going to take one tan term out. So we have this, and we can take one secant term out. So and we can isolate the derivative term, a secant tan x dx. So all the problems are going to go like that, except the last one. We always isolate the term for the derivative. Now you can write the everything else you can write using secant. So that means this one you can write secant squared x minus 1. You have to do that. And this you're going to leave because already secant. This also we're going to leave because that's the derivative term. Now we're going to substitute. So once you substitute, this is going to be u to the squared minus 1. This is u to the 6th, and this whole thing is simply the derivative. So this is du. So you can see this is very easy to do. We can distribute first and then distribute and integrate. So so let's do that now. So I'm going to skip that step. So what we do next is you're going to multiply through this. So you're going to multiply by that and multiply by this. So then you get a single term, and then you're going to integrate term by term. So you should get finally secant 9x over 9 minus secant 7x over 7. So this part is should be clear now, because we have been doing problems like that. So after you get this one, distribute and do. Distribute and then integrate. So all this problem has a special type. So you can isolate a term. So isolate a term for the derivative. Du, and then pick u appropriately. Okay. So that's always going to be like that. So you're going to pick a term for the derivative. You isolate a term for the derivative. Always, all the problems go like that. You isolate the term for the derivative, and then pick u appropriately. So you can, we discuss this like in detail in the trigonometric integrals. So you can look at that for more details. Now what we're gonna do, we're gonna move on to the rational function technique. So under rational functions, we generally use the partial fraction method. So we're going to use partial fraction method. Partial fractions method. So in short, we can call it PFM. So sometimes what happens, so let's talk about those cases separately. So let's say you have an integral fx over gx dx. So if the degree of the numerator, if the degree of the numerator function is greater than or equal the degree of the denominator function, what we're going to do is we're going to divide. So we're going to divide by the bottom function. So that's what we do. So that's a polynomial division comes into play. Uh, and then let's talk about other types with a special example. Like let's say you have a situation where you have like 2x plus 3 over some term like x plus a and x plus b, they are different. So if you get a problem like that, what we can do is we can write the partial fraction for that one. Since the two terms are different, it's going to be a constant divided by x plus a plus another constant divided by x plus b form. So that's going to be the form of that. And then, so the goal is to find a, b, and then integrate term by term. And the next one is what's going to happen. You can see some repetition. So let's say you have a numerator like that, and then x plus a, and here x plus b cube, something like that. So what's going to happen is if you see a repetition, so you're going to rewrite the one without repetition. So your fraction's going to be a over x plus a. For the repetitions, it's gonna follow the format of the smallest one. Smallest one means x plus b to the first power. That means it's gonna be like that. So that everything is gonna follow the same format, even though they have larger powers. So this gonna be b. So it's gonna be it's gonna follow the same format of the smallest one. So it's x plus b. So this is squared. And then the last one is d over x plus b cube and dx. So it's like that. So what is what you want to remember is if all the terms follow the format of the smallest degree term. So in this case x plus b has the smallest degree 1, but everything else follow the exact same pattern. It's a b, c, d. So you don't want to add any other terms to the numerator. And then the third case was let's say the fourth case actually gonna be like 2x plus 3 divided by, let's say you have x plus a, and then how about this, let's say x squared plus 4, just an example. Now you can see that this term is different because this is irreducible. That means you cannot factor this any further in real domain. So what's going to happen in this case? There's a special format of the numerator. So the first term has the exact same format as a over x plus a, no change. But for the other one, this is x squared plus 4. You can see this is degree 2. Since degree 2, the top has to be degree 1. Degree 1 means this has to be bx plus c. Okay, so that's the special situation. And then what we're gonna do, um, what we normally use, we use hybrid method. That's much easier. We use a substitution first and then equating coefficients. So we use the hybrid method to find the coefficients. Okay, so I'm gonna write it like that. So use the hybrid method. Um, uh, Hybrid method to find coefficients. Okay, because hybrid method is much faster, so that's what we have been using. um, don't just use first we use a substitution and then we use the equating coefficient technique, because in that way you can find the constant faster. So that's what we have been doing when we solve the problem using the partial fraction method. So let's try to do a couple of examples to recall what we did. But here what we normally do is we can transform a problem into that type. Okay, so as the first example, let's try this. So let's say we have 1 over 1 plus square root x dx, and you can see that you can just integrate this problem. If you just have 1 over 1 plus x, you can, but here we have square root x. So what we can do, we can use a substitution. We're going to say u equal square root x. That's obvious substitution. So this says that du equal as before 1 over 2 square root x dx. That's what you get. and then you can cross multiply. So then you're gonna get dx equal to square root x du, and then you can substitute. Once you substitute, it's gonna be 2u du. So that's what you get. So what's gonna happen now if you substitute? So it's gonna be the top gonna be dx. Dx means 2u du. In the bottom, it's gonna be 1 plus u. And you can see that the numerator and the denominator have the exact same degree. I'm going to take 2 out first. You can see the numerator and the denominator has the exact same degree, so that means you need the long division. But I'm going to show you a different trick here. So what we can do is you can try to create the denominator term in the numerator. So how you do that? You add and subtract the missing term. That means 1. So you add and subtract 1. Now you can see you can, this is like one term, so you can divide by that, so you get 1. So you can write this one as now as 1 minus 1 over u plus 1. So that's the trick. Okay, so and you can see this is the exact same thing you get when you try to use the long division, but this is a kind of shortcut to get that. Okay, so if you use the long division, you still get the same answer. So you can try that. Good. Now we can integrate term by term. So if you so you can write this if you want, you can, yeah, you can integrate this term by term. This is 2, and you can see when you integrate 1, this is u minus, and then when you integrate 1 over u plus, this is a natural log 1 plus u plus c. Now we can substitute for u. So if you substitute for u, it is 2 square root x minus 2 ln this is, since this is positive, you can just write it like that, plus c. So that's the answer for this problem, and you can see you have to use the special substitution, and once you use the substitution, the problem becomes a partial fraction problem. So good. So let's try another problem like that. So actually I'm going to give you exercise, so why don't try this problem. So let's say we have this so x over 1 plus square root x dx. So it's going to be very similar, but it can be a little lengthy. Okay, so you can try that one. Okay, so let's go to another problem. This one. So it is dx over 3x plus x square root x. Looks a little lengthy. Again, the substitution is very clear. So we're going to pick that one as u. So let's say u equal square root x, and then as before du equal 1 over 2 square root x dx. So I'm going to show you a different simplification here. So you can use the same trick as before, but I'm going to show you a different trick here. So you can see there's a square root term in the denominator. So I'm going to pull a square root term first because of that from the denominator. So let's pull a square root term. That's for the derivative part, and then we have so after that we're going to get 3 square root x plus x. So you get, so I pull square root x from the denominator. Now you can substitute. So once you substitute, now you can see dx of square root x means 2 du. So it's going to be 2 du. In the bottom, you're going to get 3. So we have x means u squared. So x means u squared, because this says that u squared equal x. So that means x is u squared plus 3u. That's what you get. And you can see this is a simple partial fraction problem. The reason is you can factor this. So you can see you can easily factor this. So it's a 2 du. In the bottom you can factor is a u plus 3. So we're going to go for partial fractions. So the partial fraction, you can write this as 2 over u plus 3. This is identical to, you can write a over u plus b over u plus 3 because those are different linear factors. So this says that if you multiply by this term both sides, this says that 2 equal a u plus 3 b u. Now a and b are very easy to find. Um, so you can see if you let u equals 0, so if you say u equals 0, if you plug in u equals 0, then you get a. So this can give a equal 2/3. If you plug in u equal -3, you can see b equal -2/3. So you get a and b like that. So very simple. So that means you can plug in them back to that. So the a equal 2/3 u and minus 2/3 u plus 3. That means you can integrate them separately now because you get the partial fractions. So you can integrate. So that means after that, then you can write the problem. So your original problem is dx over 3x plus x square root x, which is equals to, now what happened? So we have the numbers now. So it is 2/3, I'm going to pull out. It is 1 over u du and then minus 2/3 1 over u plus 3 du. So this is very easy to integrate. So you get 2/3 ln u minus 2/3 ln u plus 3 plus c. But we know that what is u, you can plug that back in. So if you plug that back in, u equal ln square root x minus 2/3 ln 3 plus square root x plus c. So that's the final answer. So what we did was we start with a substitution u equals square root x, and then we can transfer the problem into a partial fraction problem, and then use the partial fractions to integrate and then put u back in. So that's how you solve a problem like that. Okay, so that's about that. So what we did was we transform a given problem into a partial fraction problem and solve the partial fraction problems. So it's a substitution. Transform the problem to a different type. So let's go to the next one. Let's talk about the integration by parts. Integration by parts, also what we normally call IBP. Or you can also use the DI method. DI method. So you can find the link in the description if you forget what is the DI method, also for the integration by parts techniques. So here this is just a summary of what we did. So the goal is to, so let's say you have an integral which is u dv. So what we're going to do, we can use the formula, it's going to be uv minus v du. So the goal is to transform the, switch the integral, switch u and v so that the second integral is easy to integrate. So you try to find u and v so that v du is easy to integrate. That's the goal. So we can use the common trick, what we call the Layet. So it's log functions, inverse functions, and then algebraic functions, and then trigonometric function and the exponential function. So that's the order: logarithmic, inverse functions, algebraic functions, trigonometric functions, and the exponential functions. So that's the order we're gonna pick u. Okay, so we're gonna pick u according to this order from left to right. So we're gonna go this order. Okay, from left to right. That's the preference order. so pick u. Okay, pick u according to this argument. The rest of the integral is the dv. Okay, that's how we do it. Um, good. So so the basic technique is find or choose u and dv so that the integral v du is easy to integrate. Okay, easy to integrate. So that's the basic technique, and for that we can use the light argument for that technique to find the right one. So let's start with a problem like that. So we can start with this problem. So let's say we have t e negative 3t dt. So you can see that there is algebraic functions and trigonometric functions. I'm sorry, algebraic function, the exponential function. That means in this case it's very clear. So u equal t. So u equal t, and the dv is the rest of the integrals. Is a negative 3t dt. And then what we do, we take the derivative of the first one. So that means du equal derivative of t is 1, so dt. We integrate, and this exponential function, that means we're going to divide by the constant. That's how we did it. When you have a constant, it's very easy. Just divide by the constant. So the constant is this part, so we can divide by that. Okay, so we have everything we need. So so we're going to plug in. Okay, so it is uv minus v du. So if you plug in uv, that means you're going to multiply u and v, so that means negative 1/3 t e negative 3t, and the minus, and you can see there's a minus sign here, so minus minus become plus. So 1/3 e to the negative 3t dt, and then you have to finish the integral. So 1/3 t e negative 3t, and then here you can see you have to divide by negative 3 again, so it becomes negative 9 e to the negative 3t plus c. So that is the integral you get. For these kind of problems, you can also use the DI method. So if you use the DI method, what's going to happen is, so let's do the DI method here also. So we have D and the I. So D is the same argument, so t and the e to the negative 3t. So take the derivative of the first one, which is 1. Take the integral, so negative 1/3 e to the negative 3t. Take the derivative, which is 0. Take the integral, which is 1/9 e to the negative 3t. And then what's going to happen is plus and the minus. So and then we're going to multiply. So you can see according to this argument, what's going to happen is you're going to multiply with this sign, so it's a negative 1/3 t e negative 3t, and then next one is negative 1/9 e to the negative 3t plus c. So you can get the answer quickly using what we call the DI method. So that's the DI method, but there's a special video solely created for the DI method that has several more examples there. Okay, let's do a few more examples from this technique, because this is like one of the very important technique. So let's do something like which has several more terms. So how about this one? So let's say we have theta squared minus 1 cosine 3 theta d theta. So for this problem we can use the DI method, because especially when you have like complicated function like that, the DI is much easier. So D and the I. So D is theta squared minus 1, I is cosine 3 theta, because the algebraic functions comes before the trigonometric functions. Okay, now take the derivative, so which is 2 theta, integral, the cosine, that means just the 1/3 sine 3 theta. Take the derivative, it is 2. Take the integral, this sine, so it's one negative 1/9 cosine 3 theta. derivative, which is 0, integral, which is negative 1 over 27 sine 3 theta. Okay, and then we're going to start with the plus sign always. So it's a plus and the minus and the plus. Okay, since there's a 0, we don't need any more terms. So we're going to write it now. So we're going to multiply the 2. So it's 1/3. We write the constant first. And then we have theta squared minus 1 sine 3 theta. And then minus, actually minus plus 2 over 9 theta cosine 3 theta, and the last one is minus negative 2 over 27 sine 3 theta plus, and you can see that the DI method helps a lot in this situation, because otherwise you need to do double integrals here. Good. So let's do one final example of this type. So how about this problem? Let's say we have sine inverse x dx. So according to the argument, this is a trig function, so we're going to pick that one as the u. So the u equal sine inverse x, and then the dv equal dx. So take the derivative, so du equal 1 over 1 minus x squared square root dx. If you take the integral, v equal x. So according to that argument, so you're going to get uv minus v du. So uv, that means x sine inverse uv minus v du. That means 1 over 1 minus x squared square root dx. Okay, and then you can see that the second integral is not that bad. It's easy to integrate. So this is going to be x sine inverse x. So we need some preparation. You can see what is missing is negative 2. So I'm going to pull the negative sign inside, and we can write this one as negative 2x. So let's write this one as negative 2x 1 minus x squared negative 1/2 dx. So we can just use the general power rule now. So that means x sine inverse x plus 1/2. So because since we have the derivative, we're going to use the formula trick now. Because that's the inside function, you're going to see the derivative there. Just treat that function as x. So if you do that, it is 1 minus x squared. You add 1 divided by that plus c. You can see 1/2 get cancelled. So you finally get x sine inverse x plus 1 minus x squared square root plus c. So you can see the simplification goes very well in this case. So you can try these problems as practice problems. Let me see exercise. So you can try these. So why don't you try tan inverse x dx, and also x tan inverse x dx, and also x sine inverse x dx. So those are 3 problems. You can try those 3 problems. Okay, now we move on to the last type, what we call the radical functions. So let's go to that, the radical functions. So the radicals. So we're going to talk about, we did 3 type of radicals. We talk about terms that has a squared minus x squared type of term. It can be square root or some other root as well. So in this case, what we did was we used x equal a sine theta. That's you have to remember. And then in this case, dx is simply a cosine theta d theta. And then we also talk about terms with a squared plus x squared with a plus sign. In this case, we get x equal a tan theta. And then you can see if you take the derivative, it's going to be a secant square theta d theta, square theta d theta. And we also talk about x squared minus a squared. So switch the order with some radical terms. In this case, we're going to go with x equal a secant theta. Secant theta. So, and then you can see the derivative is the secant. So this is secant tan. So you're going to get secant theta, tan theta, d theta. So that's the technique that we use. And also we can use the for radical also we have a general technique also. So so you may also use in general. So when you have a term like this, so let's say some function to some kind of root. So if you see like that, generally you can just pick that the smallest root as the u function. It's gonna work. It can be lengthy, but it's also as a general rule this gonna work. So let's do one problem. Let's do several problems just to recall what we did. Uh, yeah, so let's start with this one. So let's say example. Let's do x squared minus 1 square root divided by x dx. A problem like that. The substitution is very clear. So in this case, we're gonna go with x equals secant theta. So x equals secant theta. And then we can see that the dx is secant theta tan theta d theta. So let's plug in. So once you plug in this, so you're gonna get secant square theta minus 1 square root, and then also x means secant theta, and dx is secant theta tan theta d theta, and you can see secant get cancelled. So you're gonna get inside secant square theta minus 1 tan square theta. So I'm gonna write a few extra steps here, but you can skip this. And we have tan theta d theta. And you can see this gonna be simply tan square theta d theta. But you know the tan square theta, what we can do is we can write this one as secant square theta minus 1 because you cannot directly integrate this one. Now we can integrate. The first one is secant square means tan theta. So you're gonna get tan theta here, and then minus, if you integrate d theta, you get theta plus c. Now what you want to do is we need to find the two, tan and theta. So that we can do, for that what we normally do is we draw the triangle. So we know that x equal secant theta. So that means 1 over x, if you upside down, so you can see 1 over x is cosine theta. So that means we can draw the triangle here. So this is if you say theta, so this is a cosine, that means x. So this is going to be 1, this can be 1, and this can be x. So this is going to be x squared minus 1 square root according to Pythagorean theorem. Then we can find everything here. So according to this one, tangent going to be x squared minus 1 square root over 1. We are not going to write it. So we can just say x squared minus 1 square root. And theta means you can just take the inverse. So that means theta is simply secant inverse x plus c. So that's how you integrate this problem, simply using like a basic substitution. So we use one of the substitutions for this problem. So you can try this problem as practice problems. So so as the first example, we can try 1 over x x squared minus 1 square root dx. And as a second problem, we can do 4 plus x squared square root dx. And also as the last one, we can try x squared over x squared plus 1 square root dx. Okay, so next what we can do, we're gonna try like some different examples that gonna use different technique, not just one technique but two techniques as the final set of problems. So from different techniques. Okay. So as the next general problem, we're gonna do this one. So let's say we have x ln x divided by x squared minus 1 square root. A problem like that. So so if we get a problem like that, what we can do is first we can you can notice something here. So you can see uh, so we have ln x here and also x square minus 1. So you can see that if you pick u equal ln x, if you pick u equal ln x and dv as the rest of the function, that means x over x squared minus 1 square root. This is you can integrate differentiate the first one, so that means du equal 1 over x dx. And also you can see this is very easy to integrate. So if just use the general power rule, you can see this is negative 1/2 x squared minus 1 1/2 over 1/2. In other words, you can see 1/2 get cancelled, so negative x squared minus 1 to the 1/2. That's what you get. Okay, so we get that. So that means we can use the integration by parts formula. So we can rewrite it like that. So we're going to say ln x and then x over x squared minus 1 square root dx. So this is the u function and this whole thing is the dv. So now we need to just plug in here. So so what you get is so it is uv, so we're going to multiply the two, so you're going to get negative ln x, that's the u, and the v, so this x squared minus 1 square root, and then negative positive, so you're going to get the v du. So so v du means it is x squared minus 1 square root over x, and this the second integral we already did, so that's the one we did. So and we know what's the answer for that, so we can put it there. So that means finally we're gonna get the answer as negative ln x times x squared minus 1 square root plus this one was x squared minus 1 square root minus secant inverse x plus c. So you can see you can combine them. If we combine them, so 1 minus ln x x squared minus 1 square root minus secant inverse x plus c. So so that's the final answer. So you can see so first we did the integration by parts, and then we use the trig substitution techniques to do the second one. I skipped this one because we already did the problem again. So if you get a problem like that, you have to do that within the problem. Okay, good. So let's do one last problem. So this one. So let's say we have e to the t over 1 plus e to the 2t square root dt. So if you get a problem like that, you can see you can rewrite this problem as e to the t. Here it is 1 plus e to the t whole thing squared, square root. So this clearly said what is the substitution you have to use. So you can use the substitution u equal e to the t So see, this is the du equal et dt. So after the substitution, you can rewrite this problem as the top simply becomes du, the bottom simply becomes 1 plus u squared square root. Now what we can do is you can use the trigonometric substitution here. So we can see u equal tan theta in this case. So that means du equal secant square theta d theta. So if you use that here, now what's going to happen is the top going to be secant square theta d theta. In the bottom, it's going to be 1 plus tan square theta square root. So, and you can see that this can simplifies to secant square theta. Once you take the square root, it's going to be secant theta. So that means we simply get secant square theta over secant theta d theta. So this can cancel, boils down to secant theta d theta. So secant means uh, so this is simply natural log secant tan. So this can be natural log secant theta plus tan theta. So plus c. So what you can do is you can substitute for those two now. So we can draw a triangle. So if you draw the triangle, you're gonna get theta. So this is u and a 1. So this is 1 plus u squared square root. And then we can find the 2. So that means finally we get the answer as, so you can see secant theta is et, and the tan theta is 1 plus e 2t square root. So so what's going to happen is secant theta simply becomes this is secant theta. So tan theta simply becomes e to the t. So this is going to be ln tan theta is u means et, so it's et plus secant theta. Secant theta means 1 plus u squared by u equal et. So that means it's going to be 1 plus e to the 2t square root plus c. So that's the final answer for this problem, and you can see that you use two different substitutions. First we use u equal et. That's gonna bring it to a trigonometric integral, and in the trigonometric integral we also use another substitution, u equal tan t. Those two different substitutions, and then you can see that it's gonna transform that back into that problem. So don't get confused here. There are two substitutions. The first substitution, you finally you get ln secant theta tan theta. From that, you see that we use the u equal tan theta substitution. But after you get to that, then we know that we need to go back to original u, but original u equal et. So that's why we're gonna substitute back from et for wherever you see u. So that's why this u is simply et. So that's why you get that as a final answer. Okay, now you can try these problems as practice problems. So you can try these problems as practice problems. So there are 10 problems. So for example, for the first one, you have to substitute u equal ex. So you can see that once you substitute u equal ex, this gonna bring it down to something that you can manage. The same substitution works for a few other problems as well. So you can try, so there are some problems you have to multiply by conjugate, and that's gonna make it really simple. And then there are some problems once you substitute, it's gonna bring it to a partial fraction problem. And there are also some problems they're gonna be integration by parts problems. So you can try these problems as practice problems.